Okay, please start recording. Good morning, students. Today is Friday, May 20th. We're going to continue with our review, okay? Today, we're going to review kinematic hypothesis, okay? We can establish this hypothesis. See, this word is very important. That means that we should, at the end of this chapter, we should check if this assumption is correct or not. We usually don't do it, but it is a good opportunity for doing some tests, okay? But this is an assumption, okay? The assumption has three versions. The one, which is very common, is we say sections rotate. So if you have something like this is your beam. Then we have a section like here. When you have a load, okay, this deforms up to here, right, vertically. And this section is now like this. See, it was vertical, now has rotated. But you see that it is straight. Okay, so they don't deform. The other way to say it is that, I'm sorry, some space, but no, this is incorrect. Plane sections rotate and stay plane. That's one. This is what I'm showing here. The other one is that sections rotate with respect to an axis, a transverse axis. Okay, so it's basically the same, right? So we said, okay, if we select this point here, this is the neutral axis, we see that it has rotated. Okay, so this point here moves vertically and also rotates and gets to this position. And the third one, which is the one that we are looking for, is that it's more mathematical. We can say is that the strain, okay, the strain in a section varies linearly with the vertical position. Okay, so this is the one that we're going to be using. Now here, for example, I have this dotted. This is the original beam, right? And after applying loads, this is the deformant, okay? You can see that this section, as we have just mentioned here, has rotated to this one here. Now, you see that there is a vertical distance between these two. And this is what we call V of X. That's the deflection. See, the vertical displacement. But this one here is very small, okay? And we write it here in this way because otherwise we wouldn't be able to see the differences, okay? In general, V of X is very, very, very small, right? Okay, so let me, after this explanation, let me use these two, draw these two lines down here. Okay, so this is the original on the format, and then I'm going to include here the one which is rotated. Believe it or not, this is a straight line. Okay, it's difficult for me to draw here. Let me, okay, but it is a straight line. So this is something like this. And we see that this is the elongation, right? See, originally, for example, this point was here and now it's here. So it moves in this direction. You see that this elongation varies linearly. Since we're considering this section, right, this is the original length. Okay? So we can see immediately that if this elongation varies linearly, because the two lines that I just draw, those are straight lines, okay? So this linear variation divided by the original length means that's the strain. So we can write that strain in the x direction is proportional to the distance y. So we measure y from here and vertically. The origin here, we will find out in a minute. But right now we're saying that whatever this origin is, from that point we measure y. And this assumption that the section rotates means that the elongation varies linearly with y. If we divide that by the original length by the original length, we can say that the strain varies linearly with y. Okay? Now, let's go on. Now, if instead of this proportional, we can write that this is equal to a constant. Let's call it CT, constant, times y. Okay, so instead of expressing this as proportional, we said, okay, this is going to be converted into a constant, and then we have an equality. And here, we can assume also that Hooke's law is valid. Okay, that means that we are in a region below the yield point. So we have a straight relationship between between sigma, the stress, and the strain, epsilon. So we can say that sigma x is equal to E epsilon x. Now, in general, we will see this in chapter 4. There are more elements in the stress tensor. But here, we are just assuming that only sigma x is important, okay? And only sigma x is important. Okay? So in this case, since epsilon x is this, so we can say that this is a Young modulus, this constant that we still do not know what that is and why. That means that there is a linear variation of a stress, of the normal stress in a section. So, so we expect a linear variation of sigma x with y. Okay, now there's somebody in the waiting room. These internal forces, remember, this is something that we discussed yesterday. These internal forces, they are determined from equilibrium. Okay, so this from equilibrium. Okay, now here, this is letter S, but it should say sigma. Okay, we are assuming this distribution. Okay, and thus distribution is this one. This is just an assumption, right? We're assuming that there is a linear strain distribution. This is an assumption. Okay, and as a result of that, we have a distribution of stresses. But this distribution, which is the result of an assumption, it has to be consistent, statically equivalent to this, to the internal forces. Okay, so the stress distribution be statically equivalent with the internal forces. So in this case, I'm showing P of X, okay, that's the axial internal force, but we are not considering that. We're going to be worried about, I'm sorry, P of X, yes. V of X is the one that we are not going to be worried in this chapter. In the next one, that's the main parameter. So right now, we have a distribution here of sigma. Okay, that's the result. That's the result of this kinematic and Hooke's law. But they have to be consistent with this and with that. Okay, so that means that if we integrate this distribution, we have to recuperate P of X. So P of X, remember, this is the axial force, has to be equal to, if we multiply this sigma by a differential area, we're going to have a differential force, axial force. If we integrate on the whole section, okay, we're going to have the total axial force. But the problem is that in this chapter, we are interested only in applying lateral load, vertical forces. Okay, so since we have only lateral load, P must be 0. So we can say that P, which is equal to 0, has to be equal to the integral over the whole section of sigma x. But sigma x is going to be equal to E constant y times dA, following our assumption. So we say that E and C are constant, so we can take them out of the integration of the integral, and we got something like this. There. So this integration has to be equal to 0. Why? Because there is no axial forces in our analysis. We only apply forces in the vertical direction. Now, E is never 0. If the constant is 0, so this distribution doesn't exist. So we have to look it up to this integral. So this is the first moment, okay? The area, and we can express it as a product of the A, that's the total area, times average Y. So that's the position of the centroid. And the result of this has to be equal to 0. So E, C, or A are not 0. So the only way that we can get this equal to 0 is that C, Y average is equal to 0. If Y average is equal to 0, that means that the origin of the reference system is at the centroid of the section. So from here we can say that the origin of the reference system is at the centroid of the section. So if we do this, then this equality is satisfied. Now let's go now to check that this distribution integrated produces this bending moment. Now, so now with the bending moment. Okay, now we have a section. Let's go to the next slide. This is X. In the vertical direction is Y. That's it. Now, let's consider a positive Y. Let's consider a positive sigma X. This multiplied by a differential area will give us a force. So it's sigma X dA. Now the arm is Y. If we make this product, we obtain moment. But you can see that if we have this positive, considering a Y positive position, this tends to generate a moment which is in this direction, clockwise. But the problem is that this is a positive phase. And in the positive phase, the bending moment is positive in this direction. This is mz of x. So we need a negative sign here. Okay, so this has to be equal to minus the integration over the whole section of the product of these two parameters. So this is the arm, and this is the force. But we know that this sigma we have assumed as E, CT, Y. And this is a result of an assumption. We are assuming the kinematic hypothesis. So we replace into here, and we recognize again that E and the constant are constant. So we can say that this is equal to minus E CT, the integration of, I have Y squared dA. Please don't write on the screen, people. I'm going dA. Let me go back. Here on the right, I have the first moment, okay? This is the first moment. Y was raised to the first power. But now I have something similar, but now it's raised to the second power. So this is the second moment of inertia, okay? And remember that Y is measured from the centroid. So this, we can call it I sub C. And the C means that is the Y is measured from the centroid. So the constant can be evaluated as minus the moment, and we have to divide it by E and I sub C. We're going to devote some moments at the end recalling how to calculate I sub C. And the most important is sigma, right? Back here, sigma is equal to E, Y, and the constant. So we can say that sigma is equal to E, Y, and the constant, which is here. And this is equal to minus mz of x divided by E I sub C. So we cancel the E. We have to be careful, and we can say that sigma x depends on x and y. That means that if you go along the length of the beam, you can have different distribution. And starting at the neutral axis, at the centroid of the section, you can have variation, linear variation of the stress. So this is going to be equal to minus mz of x, y, and divided by the inertia. So this is what we call the normal stress function or a formula for beams. Okay, so if we know the bending moment distribution, we can calculate the inertia of the section, and we can calculate the sigma, the stress, at different y position on the section. Is there any question here, up to here, people? Is there any question?
Yes, Doctor. Ranza, I have the question.
Yeah, go on.
Is it possible that the normal stress is negative in one case, or is always positive all case? For example,
No.
in the no.
Okay, here I have 2 points where this can influence. The bending moment, be positive or negative, right? And also y could be positive or negative. So you have several combinations. Okay, so first determine the value of the bending moment. Okay, so let's suppose right now that the bending moment is positive. So if it is positive, we have something like this. Remember, smiling, right? So we have, this is x and this is y. So this is positive. Now, if we analyze this portion here, this means that y is also positive because we are up from the neutral axis. So that's positive, but we have a negative sign here, right? So positive, positive, negative. So in this area, above the neutral axis, sigma is going to be what? You tell me. Sigma is going to be in this area. Sigma is going to be
Negative. Negative.
and that's what we call that this area is in compression. You could all the situations, right? You could have the bending moment negative, and you want to consider the lower part of the beam, of the section. So you simply have to be aware that these combinations are possible. You have to be careful with the sign, that's all. Always at the neutral axis, the stress is null. That's something which does not allow any discussion. Okay? Let me go. There is another question. Ms. Sanchez, is there any question, Ms. Sanchez?
Yes, doctor. My question is about is the normal stress is the same if I do this analyze with the negative phase?
Would you, let me step. Okay, would you repeat please, because I could.
I can hear you, doctor. Sorry.
Oh, the microphone is here. Okay, the problem is that the device from where I listen is there and the microphone is here. Would you please repeat that, your question?
My question is about this analyze will be the same if I analyze with the negative phase. So I refer to the sign convention.
Yeah. In that case, let me duplicate this. Let me duplicate this. That's a good question. Right? So, question is from Miss, I remember, is what happens if we analyze a negative phase? There shouldn't be any difference. I mean, this is X, this is Y. Okay, now if you have a positive moment, you have something like this. Right? So in this area, let's suppose that the bending moment is positive. Okay, in this area, Y is positive, right? So the formula says that the stress is equal to minus moment times Y divided by the inertia. So this is positive, this is positive, this is positive, but with this negative means that in this area, we're going to have compression. Yes, that's correct. It's consistent. The system of units of sign is consistent. So here, we're going to have this part here. Sigma is going to be negative, and that means that we're going to have compression. Is Sanchez, did I answer your question?
Yes, doctor. Thank you.
Okay, no problem. Okay. We don't get confused. Okay, so we're going to continue. Now, let's remember how to apply the calculation of this second moment of inertia. Why? Because extremely often, very often, we have composite sections, okay? So for example, let's suppose that we have a plate, okay? And here, for example, we include a T reinforcement, okay? When we have load here, so we're going to have some bending, okay? This is the longitudinal direction. And we need to calculate the inertia of that. If we calculate inertia, we can go on and apply our formula and calculate the stress. And we can say if we are safe or not. But the first thing that we have to do is this. Okay? Now, what we do is this, okay? Let's suppose that we have about here, this is the centroid of the whole section. Okay, so from here, in this direction, we have axis X, and vertically, we have axis Y, right? So in general, when you start the calculations, you don't know where this centroid is. So what we do is we take a reference line. The easiest way is to take the baseline as a reference, but you can take any line that you want. Okay, now we want the inertia with respect to the centroid, and we're going to help us with the calculation of the inertia with respect to the baseline. So from here, we're going to measure a Y, which is different than this one. So I'm going to differentiate that with a prime. Okay, so we can say that we can apply parallel axis theorem. And we can say that the inertia with respect to the baseline is equal to the inertia with respect to the centroid plus the total area times Y average. So a Y average is the distance from the baseline to an axis which passes through the centroid. So this is Y average. Okay, so if we calculate this, I'm sorry, I need a square here. Eventually, you calculate that, this is what we want. So we can say I sub c, this is what we want, is going to be equal to I, the inertia with respect to the baseline, minus a bar squared. Okay, so let's go and try to calculate the inertia of the whole section with respect to the baseline here. So this is the expression that I have to the right. But instead of integrating everything at once, you can see immediately that this section, for example, is composed of 3 rectangles. One here, plate, here, the web, and here, the flange. So in this case, for example, I have plate, I have web, and I have flange. So the integral of the whole section, we can split it into integrals of the web, of the plate, then the integral over the web, and finally over the flange. Okay, and this is what we're going to be doing. Now, here I have the summation, okay, that I'm showing down here. So the result of this will give you the inertia, okay, of each one of these elements with respect to the baseline. Okay, so for example, let's consider only the plating. Okay, this is a rectangle. Okay, so this is, for example, the area that I call A sub I. Now, I need to calculate this inertia with respect to the baseline of only this element. And what we can do is we can apply again this theorem, parallel axis theorem. So the inertia with respect to the baseline of this element, only this element, is going to be equal to what? The inertia of this element with respect to this own centroid plus the product of the area of this element times the I squared. So in this case, of course, the centroid of this element is going to be about here. So from here until here, that's D sub I. Okay? And since this is a very simple element, we can recall that this value is usually, it's something that we remember. Usually, every element has simple shapes. And we can recall formula for I sub Ci. Remember, I sub Ci is the inertia of one piece of the section, one element, with respect to its own centroid. For example, in the case of the rectangle, anybody? In the case of the rectangle, how do you evaluate I sub Ci? Name somebody.
1/12 base L cube.
No, it's close, but it's not. So it's equal to
Base to the
H
head.
to the third divided by 12.
yes, yes. So please be careful. This is the width of the element that we're analyzing. So in this case, it's going to be from here until here. The h is the height of this rectangle in this case. So it's going to be the thickness divided by 12. Okay. In the case, the other very common case is the circular. So you remember that this is equal to pi the diameter to the fourth divided by 64, and so on. So these are very simple. So what we can do is we can take a section, we can break it up in little rectangles. And after that, we can calculate the inertia of each one of these pieces, these little rectangles, using this formulation. If we know that I sub ci is equal to bh cubed over 12, and we can identify the position of its centroid and measure from the baseline. And from that point, we can apply the formulation. Okay? Any questions about these, people? Okay, so since this is a very common situation in our area of engineering, in naval engineering, we summarize this in this way. Okay, this is a table that we should always remember. Okay, so we have the first column. The first column is just a numbering. It's a good idea because if we know the number, we can identify. Please check line this or that. Okay, description is very important because if we know something of this, we can check our results. Okay, and we will go that in a minute. Here we have the breadth or the width of if we have split it into rectangles. So this is simple. So this is B sub I, this is H sub I, and here is the centroid. So from the baseline up to here, this is di. This is this one here. Now, A sub I is equal to this times that. So if you implement this in Excel, right, you immediately can implement this formula and then just drag it down, and that's it. The next one, it's the product of A sub I, this column, times this one. Again, it's just a formula, and you just drag it down. 1025, you have to tell me. And this also is very simple because you multiply this times that. And this one here, we have to be careful. If these are rectangles, this is the formula that you recall. So if each one of these is a rectangle, then this one here is going to be equal to VI HI cubed divided by 12. So in this case, we're combining these columns. You drag them down and then produce these summations. And finally, we can recall formulations. So if we need to calculate the position of the centroid, that's by definition equal to the summation of the first moment divided by the total area. And you see that this summation is here. And this summation is here. Now, we go on. The inertia with respect to the baseline is equal to the summation of the inertia of each one of the elements with respect to the baseline. So it's going to be equal to I sub Ci. This is the inertia of each one of the elements with respect to its own centroid, and plus what? AI di squared. But this is equal to the summation of I sub Ci plus summation of AI di squared. So here, I have this, here. And once we have calculated I sub BL, we know that this is equal to I sub C plus A D or Y average squared. So finally, we can calculate I sub C equal to I BL minus A. Here, I have the position of the centroid. So I can take this, put it into here. A is this is that, and we are ready. There are several alternatives to this, but I prefer that everybody works with the same procedure. So eventually we can review this. Questions about these people? Questions?
Good morning, doctor. Sorry for my question, but what is represent DI?
Mr. Llanos, what does BI represent? Mr. Llanos, what does BI represent? Llanos? Now, here we said that if we have a section, we can identify several pieces of this element. For example, this is one piece, and it is a rectangle, right? Because we see that the plate has uniform thickness and it has a certain width. So this rectangle, right, is or contributes to all of these calculations. And what we need is, this is what we saw here. We need to calculate the inertia of each one of these pieces with respect to an axis which goes through the centroid. So this formulation, we have to recall it from our vector mechanics course. This is from vector mechanics, okay? So this B is BI is the width of this rectangle, okay? So that's why I tried to draw here. So this distance, that's the width. The height is HI, and CI is the position of the centroid. Questions, people? Any other question? Any other question? No. Okay. People, we have to be careful here, okay? Because when we calculate the stress is equal to minus mz y over I sub c. Okay, so the largest value of y, okay, means that we have the largest value of sigma, okay? So, for example, in this case, we have the plate, we have the web and the flange, and the neutral axis is going to be about here, right? So, if we measure from here y, we have to worry about this point because it has the largest value in the positive sense. But we also have to check this fiber down here because there is a large distance measured from the neutral axis. It's not the same. It's not the same. But what I'm saying is that and from the neutral axis, you have to obtain or identify the farthest fiber up and the farthest fiber down. Because in both cases, you're going to have very large values of y. And of course, you could have very large values of stress. There was somebody who was question?
Yes, doctor, good morning. I have a question.
Go on, Benavides.
But what happened in the case that, for example, we have an inclination in our plates? How we can calculate that? Because in this case, we only have a straight position.
If we had, I'm sorry, if we had what?
An inclination, for example, in this case, we have in 0 great.
Okay.
But if we have
That's
an
a good
inclination,
one. That's a good one. Okay. Okay. See here. For example, you could have, for example, in the case of the ship, you can have something like this. If it is a fishing vessel, you have something like that, right? This angle. Do you remember how do you call this angle? Okay, the dead rise angle, right? In this case, okay, this plate, this piece of plate is a rectangle, right? Okay, and in this case, what we have to do is we could apply, there are certain formulations in Singer's book, in the appendix of Singer's book, and you can calculate the inertia of that plate, which is inclined, considering of the straight section, and then the amount of rotation. Yeah. Benavides, yes, in that case, yeah, you have to look it up in Singer's book.
the formula are there, yeah, in the appendix.
I cannot put so many formulas in my memory. People, for this Tuesday session, I want you to review the material for that session. Okay, so you can look it up in Popov's book. They do a combination of kinematic hypothesis, the analysis that we have performed this morning. So sigma varies linearly with the vertical. Also consider that Hooke's law applies, and also they obtain a formulation for the curvature. So they approximate the curvature by the second derivative. And with these three, they relate the bending moment with the second derivative. Okay? And that's the other relation that we are looking for to calculate or analyze indeterminate beam cases. Okay? Remember, that's something that we explained in subchapter 1.2. It was that we could apply the second derivative of the bending moment equal to P of X. That's only applicable when we have determinate beam cases. But there are many cases which are indeterminate. So right now, we're looking for this other relationship. Okay? And this second relationship is based on assumptions. Hooke's law, kinematic, curvature. Once we obtain that expression, it's like having another equation for our, and when we combine these two, we will produce and use that to solve determinate or indeterminate cases. Determinate cases because we are including in that equation not only equilibrium, but something extra. And this something extra allows us to these indeterminate cases. Okay. So with this information, let me try to. Jesus Christ. I cannot find. Can you see my screen? Yeah. Okay, the PDF. Okay, that's the homework for people that you have to start looking for. Okay, now this system here is a very simple model of a sheet propulsion system. Okay, so you like sheets, right? So you should be able to analyze this system. It's a shaft with a propeller. Is statically, so you should be able to calculate the bending moment distribution. Okay, and then on Tuesday, I can explain this thing here are the results that we obtain in a test. What I want you to do is calculate theoretically and then compare that with our experimental results. So it's 11:30. If is there any other questions? Otherwise, I will call this session up. Any questions, people? Any questions?
Doctor,
Yep.
does the shaft have any weight?
Yep. You have to consider the weight of the shaft. You have to consider the weight of the shaft, and we assume that it's uniformly distributed. Okay, so that means that the weight per unit length is constant. What's the direction of the weight per unit length of the shaft, people? Downward. So what is the sign of that? The sign of that is going to be positive or negative?
Negative.
Negative.
Negative, yes. And on the right end, you have a concentrated force.
Propeller.
So, exactly. So you have to apply that as a boundary condition, the known value of the shear force. Have a nice
And
day. See you
Doctor-
Tuesday. Bye-bye now.
in the left, we can take that it's clamped, yeah?
I'm sorry, say that again?
In the left, we can take that the shaft is clamped, yeah?
No, the shaft on the left is free.
It's free.
It's free. Yeah.
Okay.
I can share a picture of you with the experiment. Okay, I'll include that. No, there is a picture here. There is a picture here, and you can see that this is free. So we have one support here, another support here. This is the weight of the shaft, and here I have a concentrated force on the right. I have to leave the classroom because there is another class right here. So bye-bye.
Thank you, Doctor.